I use the board. I'm going to do my best not to say electrical flow, except that once. And I think I took the title of the workshop too literally, because what I'm going to talk about has to do with Spectral and is fast because it's inspired by Spectral, but somehow the content itself seems to be an outlier with respect to the rest of the workshop. So here's the outline slide. Is a new model, I think new, and then an algorithm. Sort of a surprise, and an analysis outline. That's the outline. This is, what's the title? Right, so this is subsampled power iteration. That's actually just telling you the entire algorithm. Power iteration, you take a matrix, multiply by a vector, repeat this. It gives you some useful things like the top eigenvector or something in the top eigen subspace. Subsampled, don't use the whole matrix. Take a random sample and do it. And do it with an independent random sample at every iteration. So that's the entire algorithm. Why are we doing this? So this is going to be a unified algorithm for stochastic block models, which I will define in a second, and planted SAT or constraint satisfaction problems. I should really say K-SAT, CSP. And I'll define both those problems in a minute. Okay. So both problems have the following flavor in common. They are problems over random instances. So the instances are random except that there's a solution planted. So they're biased towards a planted solution somehow. And the stochastic block model, also called planted partition, is the following problem with a large literature. There's a graph and an unknown planted partition of the vertices in the graph. Edges within the parts are picked with some probability P. Edges across are picked with probability Q. And so these probabilities are different. And you'd like to find the partition with high probability using as few edges as possible. That's it. Okay, so recover planted partition. This problem has a long literature. I should at least mention. So, 1987, Bipartite gave an algorithm for the bisection version when this planting was a bisection. Then Jerem and Sorkin used a Metropolis random walk-based algorithm. Then there was a paper by Dyer and Fries, Blum and Spencer. Alone and Kahale gave a spectral algorithm. Condon and Karp gave another iterative algorithm. Feige and Ufek, Kohauglan, Botcher, McSherry, and Wu, most recently, just this past year, another algorithm based on SVD. So it's a long literature. Some of these works I should mention not only for partition into 2, but you can also talk about partition into K and with different edge probabilities and so on. Okay, we'll talk about some of these algorithms in a minute. I do want to mention a very nice conjecture that was made, a very precise conjecture that was made 3 years ago by Dissel et al. Dissel, Kryskova, Moore, and Zedeberova. And here's what they said. If I think of P as A over N and Q as B over N, where N is the total number of vertices, then they said that recovery of this partition is not possible, they conjectured, is not possible if this is smaller than 2 times A plus B and is efficiently possible with the polynomial time algorithm if it's bigger than 2 of them. So impossible and polynomial time. So, and this conjecture was proven recently by Masuli and also independently by Mossel, Neiman, and Sly. Both parts, the lower bound and the upper bound, are non-trivial. You might wonder where this comes from. So one high-level explanation is that if you try to run a process called belief propagation on this graph and ask when does it have a non-trivial fixed point, you'll come up with a condition like this. But beyond that, I don't understand exactly why this shows up. So this is an exact threshold polynomial time algorithm. Okay. Now, what we're going to talk about now I get to the new model. So this new model, should pick a different color, is the bipartite planted partition.
So does something interesting happen for equality in the above cases?
Yeah, what can you do at equality? I don't know. I would guess that it's not known exactly what happens.
You can't recover any information about the box.
So I can make this less than equal to here? Okay, thank you. Okay. This is, by the way, it's joint work with Vitaly Feldman and Will Perkins. And Vitaly's here. Okay, so what is this model? So now you have a bipartite graph, V1, V2, and there's a partition of each side, A1, B1, A2, B2. The two sides don't have to be of equal size. In fact, I will, to emphasize that, draw this figure. The edge probability between the B's is P, and across is Q. And the goal is again, the goal, let's say, is to recover A1, B1. That's the problem. Now you can solve this with this by just identifying the two sides. So those are equivalent. But the reason, okay, so let me state a result here. Then I'll state the second problem. We'll use the same model to reduce that problem also, and the second problem is very different. And then the algorithm will come. Okay, so the statement here is going to be the following. That let me reparameterize this as follows. Let's say that the probability between on one side of the partition, so the A is one side, the B is one side, is delta P, and the probability across is 2 minus delta P, where delta is not equal to 1. So this is, to avoid confusion, I'll make this delta P here and 2 minus delta P. Okay, so then theorem, and we want exact recovery, the entire A1, B1. Order square root n1, n2 log n over delta minus 1 squared edges suffice. Okay, n1 is the size of this one, and n2 is the size of this. So, when n1 equals n2, that's linear in the size of the graph times log n, and it's a lower bound that matches that. But when n1 is not equal to n2, let's think of n1 as much smaller than n2, then this is actually smaller than the number of, potentially smaller than the number of edges in the bigger side. It's optimal up to a constant factor. And I would love to have a conjecture like this for this version, but I don't know what it is. Or if there is, if one.
Can you say just if I mean to exactly recover A1?
A1, B1.
Okay, whereas in the other case you only got like some advantage.
No, this is exact recovery as well.
Well, in the sparse case, it's only
Oh, right. In the sparse case, it's only, that's right, yeah. So here, you pick up these log n factors when you want to do exact recovery versus, yes. So that's right. So to the analog for the conjecture would be, you want to find something that's highly correlated with the partition. Yeah. Okay. So that's the first problem, and this now here's problem 2, which is looks quite different. Planted K-SAT or K-CSP. So here, let's think of a set of n variables, so 2n literals ordered. So the literals, I just index them 1, 2 to n, and 1 bar to n bar. And a clause, so it's going to be a satisfiability problem. You get a bunch of clauses, and you want to find a satisfying assignment. Clauses are just ordered k-tuples of literals. And you can do it in many different ways. If it's just satisfiability, you would say there's your clause. So it's the disjunction of these literals. But in a CSP, you might have a predicate for each clause. Somebody picks a predicate, different predicate potentially for each clause. Okay. Now, what makes it planted is that there's we first fix an assignment sigma, unknown. On the variables, and the distribution on clauses. So this is a clause. And the distribution on clauses is affected by sigma in the following precise way. So the probability of a clause C of this type, a k-tuple, is proportional to, let's say, this function given by this function q of C, which depends only on the assignment values of the literals in C. So you picked a class, x1 or x2 or x3, or x1, x2, or xk, look at the assignment values on those literals, and q tells you a number which the probability of picking the class should be proportional to. So q is a function that goes from plus minus 1 to the k to 0, 1. Non-negative function. Okay. So for example, if you wanted to pick a satisfied KCNF SAT, you would make Q have Q equal to 1 for all clauses with at least one true literal. Okay. So as long as you picked one true literal, at least one, that would be Q equal to 1. If you wanted XOR SAT, as long as the number of true literals is even, you make it 1, otherwise it's 0. And what's the problem? Recover sigma. So the problem is recover sigma. The question is, how many clauses to do this efficiently? To do this in polynomial time. Now, like in this block model case, there's a huge gap here and not a constant between what's needed information theoretically and what we can do algorithmically. So if I'm going to draw a little picture, a little plot, if this is the number of clauses, and this is, let's say, the number of surviving assignments or satisfying assignments at any point, it starts out high, all 2 to the n potentially, and there's a point here which is just proportional to n log n, where only one assignment survives, namely the planted one. After you see n log n clauses, and I'm ignoring the dependence on k here, it's a function of k, the number of only the planted assignment, of course, will always survive. Let's say we're talking about the case where each clause can be satisfied, then the planted assignment always survives.
Should we be talking about q being like the n function now?
SAT, yes, so Cn of SAT, yeah, exactly. Yes, right. We can I'll mention the analogy for the general case in a second, but yeah, so it's just a SAT case. Then this drops off, and then there's a point here, n log n, that's the unique one. But at the moment, the best algorithms for finding it need n to the k over 2 log n. So it's a huge gap.
For some Qs.
For some distributions on Q. There exist distributions on Q, and I'll mention one, specific one in a second, for which this is this line. Now, it doesn't have to be the satisfiable case. Let's say Q just picks up a bias towards the assignment. Then find the only, after n log n clauses, the only assignment that will be correlated with this distribution, you can define a threshold for the correlation, will be the planted assignment. Again, that threshold is still only n log n. Now, okay, so how do we explain this gap? Can we do better? So on. Okay. Now, let me just mention, we don't have to go into this in detail, but there is another version of this problem which was used by Goldreich to define a pseudorandom generator, where what he does is he first picks a predicate and fixes it. And then, instead of just giving you clauses, you get these ordered tuples along with the value of the predicate. So the clause, the tuple, value of the predicate, tuple, value of the predicate in this form. Okay, and the value of the predicate when evaluated on the planted assignment. So your goal is still to recover the planted assignment. So that problem has very similar behavior, although formally you have to make the algorithms a little different. I mean, not the algorithms, the analysis. Okay, so this is the mystery here. Now, the theorem, let me state the theorem here again, and then again, is the following. So to state the theorem, I need one definition, which is the distribution complexity of Q. So we'll call this the distribution complexity. It's just a single integer. R of Q will be an integer between 1 and k, and it's the size of the smallest non-zero discrete Fourier coefficient of Q. Okay. So the minimum size of S where Q hat S is not equal to 0. But this is the discrete Fourier coefficient. Which I haven't seen that certainly, right? But so it's some parameter distribution. It's between 1 and k. It's K-SAT, can't be higher than k. And sometimes it's easier to think of it as the following. It's the smallest number r for which the distribution Q is r minus 1 wise independent, but not r wise independent. Okay, so it's r wise independent, but not r wise independent, but r minus 1 wise independent. And so the theorem is that order n to the r over 2 times log n clauses suffice.
Sorry, quick question, right? So the log n factors come because of some kind of coupon collector property?
Yes, you have to.
For the existence alone, greater than Cn, there will be no satisfying assignment if you didn't put one.
The only thing is that if you only do CN random clauses, you might not see some of the literals at all.
Yeah. No,
So those can be assigned anything you want.
right, I agree. So you could have two assignments differing only in one literal.
Yeah.
And both will be satisfied unless you go to n log n plus
That's
equals coupon collector. Now n to the 3 halves, that log n also comes because of that?
No, that comes in our upper bound. That's why it's only suffices. In terms of lower bound, it's not at all clear that you need a log n.
N to the 3 halves lower bound we know for unsatisfiability, a la phi or something, right?
We don't know any lower bound better than n.
If I don't plant one, unsatisfiability. I mean, I pick n to the 3 halves random clauses.
Yes.
Then we have proofs for unsatisfiability.
You can prove refutation, yes. You can refute a formula. But that's still an upper bound. If you have...
It's only NP, NP instead co-NP. Maybe an algorithm by now, but then you have an extra login.
It's
Huh?
an algorithm. It's
It's an
actually
algorithm.
1.4, 5 of it.
Is
Yeah.
it below 1.5 now, right? Okay, so,
We use 7 different ones.
Right.
yeah.
But it's still higher than what could potentially... The algorithm, the formula becomes unsatisfiable at n.
Sure, Cn, high C, yeah.
Right. That's with no planting. Right. So this is it. Oh, I should mention, the running times of both of these are linear in the number of edges. So that's the fast part. So time in both cases is order of number of edges here, order of number of clauses. So this problem also has a large literature, so I won't try to do all of that right now. So the next thing I want to do is look, this model, the algorithm in fact, is to first reduce this problem to the bipartite planted partition and run the algorithm to find the partition. Okay. So next I'll describe the reduction from planted SAT K-CSP to partition. This is in some sense, this is folklore. I mean, there's a special case for k equal to 3 that's in a paper by Bogdanov and Chow, and then there's an extension by Applebaum, which is maybe it doesn't appear anywhere, but it's attributed to him. He came up with it. So I'll describe it.
There is this paper by Moses or Rollins or you which has similar flavor, except that they're able to do the Fourier degree and the GF2 degrees. So can you get something like this? I mean, so
The minimum of the two?
yeah,
Right. No, this.
because the minimum can be high. For instance, for the parity function, it's as big as k.
Right. So R can be k. R can be k, yes.
But they could still beat the k.
So in the parity case here, you cannot read the k, as far as...
You can use if it's an exact predicate, then you can use algebraic degree. We're here taking... that's right, but we're talking about general distributions where sort of they're rarely an exact predicate. So yeah, so if it's if the distribution happens to be an exact predicate with low algebraic degree, then like in the parity case or more generally you can do it then, yeah. So
Okay, so the reduction from planted, let me do planted K-SAT to this bipartite planted partition has two steps. The first step is to reduce planted K-SAT to a particular distribution, which is noisy XOR SAT, R XOR SAT, where R will be the parameter of whatever distribution we have here. So we have some distribution Q on the clauses to start with that has some R, and we'll reduce it to noisy R XOR SAT. So that's the one step. And the second step is just that noisy XOR R XOR SAT you can embed into as a bipartite plant problem. Now the first step just follows from the definition of Q. So what do we know about the definition of R? What is R? It's the smallest non-zero Fourier coefficient. So if I write down what that is, there is some subset S for which this is not zero. Let that be S. So this is the expectation overall. So it's 1 over 2 to the k, the assignments, the sum of the value of, so x is a plus minus 1 vector, times, the polynomial here, which, let me just write explicitly, I in S of xi. Right? So this is the term corresponding to S, and that's, so. But now,
What is K?
K is the width of the clause, the number of literals. So a clause is picking K literals from that. Okay, so what is this? We know this is not 0. Let me just separate it into the terms for the even parity and the odd parity. Right, so this is exactly times the sum of Q of x, where the number of, so let's look at the absolute value. The number of xi's that are equal to 1 is even, minus the number of xi's equal to 1 is odd. Because that's the only thing that changes the sign. Right? Now, so xi's in S. That's important, right? The i's in S, those are all that matter for this. So you're looking at how many i's in S are even, how many i's in S are odd. That gives you the function. This is not equal to 0. So these two are different. So now here's our reduction. What we're going to do is take a clause, look at the literals that are in S, pick out those R literals. That's your clause. That's your clause for the noisy R XOR SAT problem. Take a clause from the original distribution, pick out the R literals that are in the subset S that has a non-zero coefficient. That's your clause. In some cases, you could just try all possible S's if you wanted, because it's only k to the R of them. But let's say the Q depended only on the number of true literals, and you could even just pick a random subset of R out of the K. So anyway, this is it. So that's the reduction to noisy R XOR SAT.
I don't know what noisy XOR.
Oh, I'm sorry.
Noisy R XOR SAT is yet.
Oh, okay. So this is the problem where you're given clauses, and I just have to define the distribution. If you look at the XOR of the literals, the probability that it's so Q of x depends only on the number of true literals in x, and it's equal to delta p if the number of true literals is even, and 2 minus delta p if the number of true literals is odd. And delta is not equal to 1. So there is some difference between there's a bias towards one parity or the other. And the predicate is just XOR. If the delta was 0 or 1, this would be the XOR problem you can solve by Gaussian elimination. Here it's the noise, each clause. This seems to be the root hard problem in this whole business with the planted satisfiability. Okay, but once you stated this problem, it's starting to look like the bipartite, maybe. At least I put in parameters that look like it. Okay, so let me do the second step of the reduction, which is we have an instance of this problem. You're given clauses. They're true. The probability you pick a clause with an even number of true literals is delta p. The probability you pick a clause with an odd number of true literals is 2 minus delta p. And your goal is to recover the assignment under which this distribution holds. So how are you going to do this? Well, we'll define a big graph, right? So the graph is going to have size n to the r over 2. So somehow n to the r over 2 has to be square root n1, n2. So the graph will be, the set V1 is going to be the set of all r over 2 floor ordered tuples. And V2 will be ceiling r over 2 ordered tuples. So if it's okay. So Yeah. If I draw this matrix, which goes from V1 to V2. Now, what's the planted partition? I'll tell you what the planted partition in this graph is. It's a huge graph. The graph has size n1 equals n choose r over 2 floor, and n2 equals n choose r over 2 ceiling. That's the size. Now, the partition is just based on the number of true literals, the parity of true literals in this subset. So here is A1 and B1, A2 and B2. So these are all the literals, I mean the R over 2 ordered tuples, which have an even number of true literals. And this is odd number of true. Same here, even number of true, so an odd number. Now, if you look at this here, a clause here, if I just think of it as a concatenation of this R over 2 floor tuple and this R over 2 ceiling tuple, I get an R clause. And that R clause, if it's even and even, must be even. So the probability of picking something from here is delta P. Again, odd and odd, this is even, so this is delta P. This is 2 minus delta P, and 2 minus. Those are the probabilities in this matrix, which is exactly the setting of the bipartite planted partition problem. Next, so we took each clause, and when you pick a clause, you get an entry here, because these are ordered tuples. So if you can now, if I recover this partition A1, B1, how does that give me the assignment? Well, once I recover this partition A1, B1, I know these clauses, and I know their parities, and I know them exactly. So now it's just Gaussian elimination. I take n of these, write down linear equation system mod 2, and solve it. Just single n. There's no, it's much smaller than n to the r. Because each of these is saying, look, for this clause, let's say x1 up to xr over 2 floor, the number of true literals is even. So I know the parity of that system is 0. And then I get it. So the last step is Gaussian elimination. Okay, so that's the whole reduction. Now, I'll now in this talk, I'm just going to focus on the algorithm, the upper bounds for these. But I do want to take a minute to mention that we have the following lower bound for this for the planted satisfiability problem, or the planted K-CSP problem. The lower bound is not for all algorithms. It's for a class of algorithms that are called statistical algorithms, where you don't get to see the clauses. Instead, you get to evaluate functions on the clauses. You can do this either by saying, what's the value of this function on a random clause from the distribution, or give me this function value within this accuracy. And in this restricted model where you don't get to see the clauses, but you can only evaluate functions on them, it seems that we can run almost every algorithm we know except Gaussian elimination. So I won't go into the details of the model or even the lower bounds, but in that setting, the algorithm we're going to provide here is optimal, and you can't go lower than n to the r, well, n over log n to the r over 2 clauses. So if there is a better algorithm that uses fewer clauses, it's going to be something that's not statistical. If there's questions or time at the end, I can discuss that more.
Just to think about the case of this that I usually think of, which is where we're doing actual SAT, like Q is and. Okay, then I guess this discrete Fourier coefficient, even the first of them, is non-zero. So what the heck happens? Something.
So the point there is that you get very. It becomes unsatisfiable very quickly, assuming there's no planting at all, or even if there is a planting, only one survives. Yeah.
Okay, I'm just trying to figure out doesn't that mean anything with this construction? Or if I do majority, let's say,
Yeah.
I can make the first coefficient, the zero order term, 0, but not the next one.
Right.
But somewhere this graph thing has to break down, right? Or no?
Which graph thing?
I mean, if r is equal to 1, what the heck?
Oh, if r equals 1. So yes. So r equal to 1 case, you can recover most of the partition, most of the assignment, using only root n log n clauses. But to recover it fully, you need to see n log n still.
Then satisfiability, isn't ours 0?
So it has to be.
You mean it's just uniform with no planting at all?
Sorry, I mean Q is, I see, I see what's going on. Sorry, I don't mean, if you just have a bias towards like having satisfied clauses opposed to unsatisfied, or...
That could still have any r depending on the depending on the distribution.
Okay, but you're saying we can make distribution, but okay, I'm
Yeah.
trying to understand what happens when...
Yeah,
I guess
so-
when we can have distributions where r is 0, right? And you can't get much out in like log n clauses.
Right. So this only makes sense when r is at least 1. Yeah.
Oh, you did specify that.
Yeah, it's
Okay.
r between 1 and k, but
1 and k.
it has to be non-zero.
Yeah. Okay.
Yeah, if the function is constant, then yeah. So planted SAT would be you're picking. This is say the true literals. These are the false literals. Your clauses are hyperedges. You're picking at least one from the true side, but you could still have any distribution you wanted on these. And in fact, you can come up with distributions that are completely satisfiable, but the r is k minus 1. So, yeah. Not the uniform case. If you just pick uniform satisfiable with at least 1, then r is only 1. But if you did this, then.
Sorry, did you say that is there a regime where you can prove the statistical query algorithm will not work and this will work?
No. So all algorithms for which all the upper bounds right now are above the statistical lower bounds. The statistical lower bounds look like n over log n to the r over 2.
Or n over log n, okay,
The log n inside the r over 2. N over log n to
to the r over 2.
Yeah. And the algorithm we'll describe now is also statistical.
No, it
Can be made statistical. This last step, yeah, but you see, by that time, we're using Gaussian elimination on information that we completely have. The algorithm has recovered. It's not Gaussian elimination on the clauses. So we can do whatever we want. It's just the interaction with the distribution is through functions.
Yeah. So the whole algorithm is a statistical query.
Yes. Okay. So let me describe the algorithm now, which you've already seen, but I'll just make it the size. Something like this.
The algorithm for the bipartite.
Yes. The bipartite planted partition. But actually, before that, I promised a surprise, and here is the surprise. So we get an instance of this matrix. We can think of the input to the bipartite planted problem as it's the same as a matrix where there is a partition, and you have random edges from this distribution. Right? These are the expectations of each entry. So if you get the matrix M, I can think of it as the expectation of M, which is exactly this matrix, plus some random matrix, right? The deviations. Now, the typical spectral approach, which is common to many of the previous papers, is the following. We say, let's look at the norm of this decomposition. And as long as the norm of the expectation is much higher than the norm of the random part, by finding the top eigenvector of your instance, or the top singular vector, it will be something that's biased towards the expectation matrix, and that's how you'll recover a lot of the partition. Okay, so this is how Alon-Kahale or Beck-Shari's algorithm or Wu's algorithm work, for example. So in this case, if I look at M minus expectation of M, but just to make this a little bit, what I'll do is, let's call this matrix the actual instance, the adjacency matrix A, and let me define M as just a slight centering, A minus we'll move it a little bit, P times the all ones matrix. Just this. So if I do that, then the expectation of M looks like delta minus 1P, 1 minus delta P, 1 minus delta P. So it's just rank 1. It's a rank 1 matrix now, the expectation. And this is what you'd like to recover. Delta is not 1. What's the norm of this expectation matrix? So it's rank 1, so it's the same as the Frobenius norm. So that's square root of, there's n1 times n2 entries. And then there's delta minus 1 squared P squared. Okay, so that's the norm of the expectation. Okay. Now what about the random part? What's the 2 norm of the random part? You see, the random part has norm that depends on the bigger side of the matrix. If it's n1 by n2, depends on the bigger side of the matrix, and it has norm basically square root p n2.
You have to have mean 0, so I guess the centering is...
I already centered it, right? So m minus em is 0. This is the expectation matrix. So m minus em has mean 0.
I see. But for computation, you don't know EM, so...
No, not for computation. This is just, I'm just saying, arguing, yeah. So we'd like to find something correlated with this vector. It seems at the least the norm of this vector should be higher than the top eigenvalue of the random matrix. Otherwise, how could you possibly find it? The noise is dominating. But if you look at that equation, which says square root n1 n2 delta, let's ignore the delta minus 1 times p is bigger than square root p n2, this is requiring p to be, at least I square both, n2 goes away, 1 over n1. Okay. P, remember, is the probability of an edge. So the number of edges is this times n1, n2 is about n2. Not square root n1, n2, but n2. So potentially much higher than the lower bound. Or more importantly, if our p is only about 1 over square root n1, n2, then the random part actually has more noise, bigger norm than the expectation. So finding the top eigenvector might give you nothing. Actually, we don't know that. Just can't prove it. So how could you possibly recover this when you're damping with noise that's much bigger? It's order of n to the 1/4 in norm. Okay, so here's the algorithm. Just use a parameter, say L equals 10 log n, 1. And we'll have matrices, so M1, M2, all the way up to ML. These are independent subgraphs of the input. Okay, so basically take each edge and assign it independently to one of these copies. Now to make it perfectly independent, you have to do this little trick where you might have to make copies and do it, but let's not worry about that. So what you can do is, you have the input which has as many edges as we said we need, and take every edge, assign it independently to one of these copies. Then remember that Mi...
They're a partition.
Yes,
Okay.
yes, they're a partition. But a random partition, yes.
Okay.
Now, all I was saying is that when you make it a random partition, they're not quite independent.
Right.
Even though they're almost that. You can force them to be independent by playing a little trick and by duplicating some edges and then. But that's just for analysis. Okay, so Mi is AI, the adjacency matrix, minus this probability P over L times the all ones matrix, just as we centered here. That's just moved everything away. Now, we initialize, we start with a random vector, which is just a random unit vector, 1 over square root n times random plus minus 1 vector. That's the initial vector. And then here's the iteration. Repeat for I equals 1 to L over 2. Yi will be m2i minus 1 transpose xi minus 1 divided by its norm to make it a unit vector. Xi will be and then Zi is the sign of xi. So this is a vector. Every coordinate is a plus minus 1, just the sign of this vector. So it looks just like the power iteration, right? I'm doing x and y. I do y is mx, x is my, but each time we're using a different independent matrix. Subsample of the original. And then step 4 is just take a majority vote of the zi's after the first log n steps. So for I equals L over 4 to L over 2, Uj, say, is equal to the sign of the majority of Zj, Zi. So in other words, I can sum up the Zi's and sign of the sum of the Zi's. This step is just implementing a majority, but not the first few iterations. Let's say the second half of the iterations. And we output the partition given by this UG. So that's it. Output partition given by U. So that's the algorithm. Okay. Now I'll.
So the surprise is you can tell us this does something that just
Yes.
multiplying by m and m transpose repeatedly.
Yes.
We can't figure out. Yeah, okay, that counts.
Well, I mean, we shouldn't be able to do this, right? Because if this works, we'd say, why not just fix the matrix to be the entire matrix and do the power iteration? Why bother to subsample here? That should only create more error. And if you just fix the matrix and did this, then you should be getting something that's got nothing to do with the, you pick up the top eigenvector of the random noise. Yeah. So if you stop after log n iterations and just take that vector, the sign vector, you'll have 3/4 of the partition correct. The majority just makes sure that you get every coordinate right.
Yeah, that's fun to achieve everything.
Yes. Yeah. Okay. So I'll just in 5 minutes sketch the outline of this analysis. Oh, in case you're wondering why is this linear in the number of edges, x is short but y is long. Y has length n2. So we cannot afford to compute y for the entire thing. Y is the long vector. And the long dimension, the number of edges is only square root n1, n2. The long side is n2. So we cannot afford time linear in this long side. We can only afford time linear in square root n1, n2. So to make this linear time, what we have to do is, but the point is that most of the y's are zeros. I mean, if the number of edges in your graph is only square root n1, n2, most of your vertices are going to have no edges at all. And all you need to do is be able to look up what are the edges adjacent to a vertex that has at least one edge. And for this, you can use this classic data structure of Friedman, Komlosh, and Semeredy from '84, I think, where they show how to implement a sparse table efficiently. You can create this table in size order of the size of number of edges, and you can look up in constant time. So that's all we need to implement this part. Yeah, so this is what you'll achieve, but you won't actually do this multiplication because otherwise it'll be too long. Okay. So the analysis is just 4 steps. At least at this level of description, it's easy. Phase 1. Okay. Oh, we keep a potential function. There's a potential function that's going to go high, almost monotonically, not quite monotonically, almost. What's the potential function? The potential function is just the inner product of the current u vector, which is the sign vector, the current sign vector, with the true partition. So actually, let u be the true partition on the left, u dot xi. This will be one potential function, and the other one is for the other side. We have to keep both growing to show that each one is growing. V dot yi. Right, so the vectors we have in the algorithm are xi and yi. U and v are the true plus minus 1 vectors denoting the partition, and this is the inner product. So we'd like this to be very high in magnitude, both of these. When it's n, then you're, yeah, okay. So in phase 1 of the algorithm, in log n iterations, log n1 iterations, ui will reach log n1 with high probability. Each of these things is with high probability.
Sorry, so quickly, what you're going to do is that u is mi plus 1 is independent of u. U is a fixed vector as far as mi plus 1 is concerned. We haven't used mi plus 1 yet. Let's say whatever u is, right?
U is just telling you what the planting is.
Up to the stage, well, or in the vi, or whatever.
You mean the xi and yi? Xi.
Up to the I stage, I plus 1 is independent. Mm-hmm. So the random part of I plus 1 makes a small dot product, much smaller than the top singular value, because it's a fixed vector as far as this is concerned.
Right.
That's how you're going to beat this.
Yes, basically. I mean, at each step you should win. The only thing we need to make sure is that you win over sufficiently many steps so that you actually recover planted partition. So the algorithm, you run this up to log n, and you stop. Now, if you were to keep going with the same set of matrices, you're going to go to the top eigenvector, and I don't know if that's any good. If you keep sampling and doing, you'll be fine. You'll stay high. But so you see, if you just do the top eigenvector, then you have no idea what that's going to do. Okay, so in the first log n iterations, this u1 will get up a little bit, and phase 2, and when it's between, then it starts doubling. Ui doubles the magnitude of ui till it reaches square root n1.
Just to fix normalization, so you
Yes.
start out with, so you use a plus minus 1 vector.
Yes.
And
Yeah.
0
Is a unit vector.
Plus minus 1, so you divide it by 1 over n. So you start out about constant.
Exactly.
Okay.
You start out constant, you have to get up to root n1
Then you get to log n, then you get to, okay.
Right, exactly. Start out constant. Right. So it doubles till it reaches root n1. And then in phase 3, once you have high inner product, every step, the zi plus 1 agrees with either u or minus u on 3/4 of the coordinates. And so, of course, then this implies that majority works. Now, this phase 2 is roughly what Ravi was describing. If you just write out the iteration, because of the independence, if you already have some correlation with the planted assignment, that's the part that carries you. Instead of doubling, you can make this as high as you want by making the edge probability a little higher. Now, the first phase is the slightly tricky one, because in the first phase, what we really have within this are two little claims. One claim is that at each iteration, independent of what else is happening, with probability at least half, ui is at least half. So it doesn't go below at least 1/4 in our paper, but it stays at least a constant at every iteration, no matter what it was before. That's just because of some variance that it has. At each step, there's enough variance because of the independence that when you run it, you get at least constant correlation. Okay. But then you also have that with probability at least half, ui doubles. Okay. But it's only probability half. So what we need is a sequence of a streak of log n1 iterations where you get the first one is at least a constant and the rest double. But out of log n, you will always have log n of any kind of streak that you want. And so that's the streak you need to get up to log n1 correlation. And then after that, it's high probability. Every iteration doubles with high probability. Yeah. We just use, so the proof requires that we maintain we have to take this hypothesis and expand it into 8 different conditions in an induction, but they're all elementary. The norms of x and y, and the norms of mx and my. We have to maintain the infinity norm, the 2 norm, and the 4th norm. And those help each other. So that's as much detail as I thought I would go into. I think it's a very puzzling open problem as to what the real complexity of planted satisfiability is, and whether this algorithmic gap is some explanation we can provide that maybe matches a physical phenomenon, like people have done, or at least suggested for satisfiability when there's no planting, where it seems to correspond to some fragmentation of the solution space. Here, less clear why there is this gap, much bigger gap between n and n to the r over 2. In our paper, we have concrete distributions that we conjecture are hard, explicit ones, even satisfiable ones. So those are also, I think, potentially good candidates for trying to prove hierarchies work or whatever you have, any other algorithm works. I'll stop there.